Okay, so the sprinter's weight is given, and it says that uh, he or she runs the first 7 meter of a race in 1.6 seconds, and he starts from rest, and the acceleration is uniform. So we need to find the speed at the end of 1.6 seconds. So what we can do, we can use this equation. If we recall, s is equal to ut, equation of motion, at square, a being the acceleration and u being the initial velocity, s is the distance traveled. So initial velocity is 0, so this one becomes s is equal to half at square. From there we can write a equals to 2s over t square, and s is 7 and t square is of course 1.6 squared. The result I got is 5.46 meter per second square. So we need to find the speed after 1.6 seconds. So v equals to u plus at, since it's acceleration, even in the previous case it's plus sign here. So again, u initial velocity is 0, so this is becoming 5.46 times 1.6, which I get approximately 8.75 meter per second. So that's the velocity, speed. And then it says kinetic energy at the end of 1.6 seconds. So that will be, since we know the velocity, the kinetic energy will be, if we say kinetic energy, that will be half mv square. Now weight is given, so 670, I believe 670. So weight divided by 9.8, weight divided by g is the mass, and times here 8.75, this one, which is 2617 approximately joules. We can write 2.6 kilojoules. So that's the kinetic energy. Now the last part is, what average power does the sprinter generate during the 1.6 second interval? In that interval, what is the average power that the sprinter generates? So this is the kinetic energy towards the end of that. So initially the kinetic energy was 0, and then towards the end it's 2.6 kilojoules. So that much work is done in that time interval. So average power will be the work done in that interval divided by the interval time. So that will be 2.6 kilojoules. So maybe I will write what I got there before, 2617 approximately, and then divided by 1.6. So that's 1635 watt, or we can say 1.6 kilowatt. That's the average power generated by the sprinter.